He's a professor of industrial engineering and operations research at IIT Bombay. And his current academic interests include sequential decision models like reinforcement learning, multi-armed bandit problems, Markovian decision problems, and other operations research methodologies like learning algorithms, game theory, etc. He's also interested in the applications for resource allocation problems arising in the context of fields like supply and value chains, communication networks, logistics, and so on. So a big round of applause to Professor Hemachandra. Welcome you.
All right. Good afternoon, everyone. Am I audible? Yes. All right. Yeah. Good afternoon, everyone, and thanks, Dr. Shantala, for a generous introduction and probably a bit embarrassing, in fact. Okay. Thanks to Shalab and Gugan for inviting me for this. Yeah, these type of activities are actually useful to the community in general, primarily various types of students and others also, what industry and academia. I understand that I think this was made possible by sort of what is called corporate social responsibility grant from Walmart to IISc. But that some industries are supporting academic research. That's good. All right. Okay. With these general things, we get started. The idea is somewhat sort of really advanced state with my former PhD student, Shan Trivedi. This is a joint work with him, and right now, this is a sharp and his thesis, which is on the main multi-agent reinforcement learning. We are fine-tuning this, and right now, Prashant is with massive. I don't know much about this company, but keep hearing about it. Our former students work in this One Network Enterprises, which apparently is a massive logistics company all over the world, US based. All right, that's the background, and all right. So the theme is some aspects of differential privacy in the context of MR. All right, decentralized MR. I don't know whether I wrote in detail about various ways of modeling multi-agent systems. So we focus on decentralized thing. But anyway, I'll spend a few minutes whenever we read it. All right. Yeah. Okay. So this is a bit old news item. From I think it's from Economic Times. I think. Well, apparently, almost a year back, Google had a data breach. I'm not. To be frank with you, I'm not tracking what actually happened subsequently, but nonetheless, these are many motivations. We keep hearing that there are a lot of data breaches. I'm not taking any stand on it, but we keep hearing that that there are data breaches within India itself. We have to host, actually, India hosts massive data sets, primarily humans, primarily Aadhaar and many things. We keep talking about this. All right. So, okay. So, this data privacy is an important aspect. We have data now about personal information like health information and economic status, whether you have a loan or don't have a loan, or all sorts of things. And many of these companies these days are very serious about it, because there is an issue with the data integrity of the data that the hosting or housing, how they have collected it. It's the nature of the things that the reputation of that company is not very great. So that's why many companies, I believe, are actually interested in this aspect. They want to protect, even in fact, formal undertakings that the data will be used as needed, and not breached or not leaked either formally or informally. Yeah, that is one. Okay, so this is not easy. Ensuring data privacy is not easy because yeah, it is loosely speaking, there's an arms race here with these cyber attacks going on in one direction and community trying to come up with more and more rail guards for data protection. So this is actually a sort of arms race. According to this arms race, and it will be there, I think, unless something radically happens. All right. Yeah, it is. Yeah, you see why this is happening is that So what I noticed is sometimes. I mean, one thing. Feel free, particularly students, just interrupt me at any point of time and clarify. Feel free that I will try to cover as much I wanted to intended, but that doesn't mean that I should keep going in one direction. Try to make it interactive and that can actually help me and definitely probably help you. Feel free to just interrupt any point and then ask some questions. Okay, yeah. So what I'm saying is that many years back, I noticed that why is this? It's a general aspect. Many of you are aware of it, but just repeating it. According to me, there is a lot of collection of data availability, primarily because the sensor technology has significantly improved the last 10 years, 10 to 15 years. My reading is that I work on some other problems. It is RFID tags. They started this about 15 years back, roughly 15 years back. The RFID tags started collecting data, and then came the QR codes, automated data collections. And and of course the storage is relatively technology side is easy. So we have more capacity for chips to hold the data. That's a matter. So basically, the collection and storage is technology driven significantly, and that is one aspect why you have so much of what I formally call a deluge of data. There is a deluge of data these days, and I think it will keep on growing. A sort of informal statement related to this, I used to say to some of my students earlier, there is a deluge of data and sort of ambitious statements. What is the wisdom in it and what is the knowledge in it? I think that's roughly to me is the so-called machine learning and AI sort of goals. Roughly, the deluge of data. What can you say about it? What's the information in it and what's the knowledge about it? All right, yeah. So in this context, there is a security measures. There are many things called encryptions, protocols. There are many. It's not that there are no methods for data privacy, but these are the challenges. Yeah, in fact, there are 2-3 known approaches. One is you sort of really mask the real important element of the data in a data set, what you feel is important indicators, what the separations, just remove whatever you feel is important or private, and then go about. Use other portions of the data only for your task, whatever could be the task. So, for example, the main items is anonymizing. In fact, the word will be I will be using this like slightly different context, but roughly that is what it is. You will anonymize the names, for example, of people if that is not very important for the task on hand. And you can anonymize maybe the gender or something like or socioeconomic status if that is not very crucial to the task. So this is actually context dependent. The point is that you have sort of certain tasks and certain aspects of the data are relevant to you and very important to you. Some are not. There is no, according to me, there is no universal answer to this type of question. It's context dependent, task dependent. And I think accordingly one has to do approach this data privacy and data. That's my reading. All right. Coming to this, you can avoid this what about suppressions, or you can aggregate data at a high level. When you summarize statistics, the mean, the mode, something like that. If that is adequate to you, the question is adequate to you or not. That's the question. That is the case. This can go hard. Suppose you are just interested in the ratio of, boys and girls in some sense. Only ratio is important, not aggregate numbers. Then just do the ratio, not even the total numbers. If the ratio is just adequate. And there is another way. About 10 years back, I think many of you.
Can you give example in context of medical data?
Medical?
Medical data.
No, I couldn't get your question. You are asking for
How this kind of site will be it's for medical.
which one?
How like what question I know, but
Yeah, I mean, okay, so yeah, I don't know whether I am answering your question or not. If it is a context of whether person is diseased or not, probably it doesn't matter at a certain level who individual is there. We just know that we need to know only the total people who are diseased and total people who are not diseased, or even this ratio. Sometimes it is adequate. Depends upon the context and the question task. That is one interesting. That is what I mean the summary data types. It's about the question that you are trying to do. Even though I should point out to you that it is well known in many contexts, like the medical, since you mentioned this point where my former students have worked on this. It is hard to design classifiers for this type of settings. And another setting is the fraudulent transactions on what is that? Debit card, credit cards, or even the UPI type of things. Because the point is that you have imbalanced data sets. Many people are healthy, very few people are diseased. Many transactions are genuine, only few are fraudulent. So people have been designing classifiers to predict whether this transaction is genuine or not. But that is hard. Similarly, it is hard to design classifiers in the context of disease or not. So it depends upon they have other problems. That's the point I'm saying. But probably probably it addresses some of your questions. All right. So aggregation is not great. And now the approach we are going to take is the other approach to this piece of work, what we call perturbation, that is add what is called noise to the data. Okay. Okay. So why is this? I mean, each approach has its pros and cons. The first two are actually there are methods, reported methods in particular. What people said that given that some data is hidden or masked or something like that, with auxiliary elements of the data, one can trace back the identity of the person, for example. Roughly speaking, it can be done. So that is one reason people don't want to do that. I mean, in the sense that if you do that, that will be the issue. All right. And as I said, there is a privacy and data trade-off. In general, some of this we actually will see in our measures as well. We try to point out what is the trade-off here. And then there are other methods where you keep on saying that that context may tell you that a lot of information that is the data set is collected is should not be disclosed in some sense. Then you keep masking it at a very high level that will bring down the value of the original task that you have. So there is a trade-off here. So some of them we try to address. I'll illustrate in our case what exactly is the trade-offs. All right. Yeah. Any other questions? Actually, I didn't even get into the details here, so let me maybe have to speed up significantly. All right. Yeah. Okay. So I think roughly I mentioned about it. Yeah, there are formal laws now. Even India has this. Primarily, I think it is a couple of years back. This was done, passed by Parliament. At a very aggregate level. In fact, there is a commission for that. Data personal protection, digital personal protection data, and then the European version is there. So this influential work is by Cynthia Dwyer. I think I'm referring to here one summary of that because I think it is written a subsequent 1 or 2 years later. She wrote with Aaron Roth. It's actually very compendium and scholarly work. But the area she has introduced this idea, what is called locally differential privacy. That is essentially you take a data point and change one aspect of it. There is a lot of data for each data point. Many other data aspects or fields along with this gender. So you change only one of them by randomized algorithms. Locally differential privacy asks this question that is there a way to change in a certain way by randomizing the data, adding noise to the data, such that the original data set on the left and the nature of the data set on the right, after anonymizing it by noise, is similar in certain sense. That's the goal. Can you design such noise adding mechanisms? In fact, that is what they use, noise adding mechanisms. okay. So this leads to the notion of what is called privacy loss they introduced. So yeah, CALM is the randomized noise adding mechanism. There is an auxiliary data and a data point D, and you want using this data sets, you want certain output O, and yeah, then you the D will give you one output. Essentially, everything else, but perturbed D dash will give you should give you the same output. What is the probability of they being tallying in some sense as long as the outputs are tallying? This is looking at the ratio of the probability that the end result of without and with noise adding mechanism is the same. Wow, same output. What's the probability of this ratio? So this ratio being more than one, less than one, that leads to the idea that we should add a log to it, and log being a monotone function that doesn't change the nature of roughly speaking, and look at the mode of it, because log can be positive, negative, different, plus than or more than one. So yeah, then this is what is called privacy loss. This computes. That's how for a given data privacy noise adding mechanism talent one computes this privacy loss. Am I clear? So one tracks this utility of your mechanism in some sense, how good it is by this measure. This is one way of doing it. All right. So yeah, the LDP, yeah, in a sense, okay. So maybe I will just yeah, this is easy, but let me just motivate a couple of other aspects here. Or maybe I'll try to do it a bit later. So if you sort of take simple, yeah, take a, I mean, use the fact that log is a monotone and then convert it, you will get this type of implication, which involves the inequalities in the probabilities of the original data and the perturbed data, that it is e power epsilon plus delta. So one can achieve this. Of course, with a finite data set, we can't achieve exactly. We want to achieve that with an epsilon loss with high probability. That is the motivation to write in this way. This is actually the high probability bound. That the C, I mean, the C is less than the probability that the C is less than equal to epsilon is at most 1 minus, at least 1 minus delta. That's a high probability bound that I mentioned. So we'll get this type of motivation. Right. So these epsilons and deltas is epsilon is the tolerance level, and the delta is the high probability leeway that you are going to give user given privacy parameters. And yeah, these are du is the original data set, and du dash is the perturb or noise adding mechanism thing. This community uses the word called users, so I'm sticking to the user notation u and the phrase users. In our setup, the users will be something else later. Okay, this is simple. Let me tell. Yeah, I think maybe I'll just keep this, but give you the idea about what's a way to go about it. Suppose you have a large data set of a large cohort community, and height is mean height is what you want to track in some sense. Then yeah, we feel that, say the context says that the exact values of the height have to be protected. Then one simple way is that anonymize them. What they mean is that yeah, add what is called noise, say uniform between -1 and +1. Sample from uniform -1 and +1 and keep adding to it to observe original heights. So then you say that yeah, this is LDP example. You have a mechanism which protects the original values of heights. Why is this leads? This is the motivation, and this leads to the next question. Oh, sorry. I think I should do it this direction. Oh no. Yeah. Okay. So the mu is a so-called population mean or the distributional fellow, and ud is what the sample mean you computed from this original fellow. And what the relation between these two will be, there is an epsilon, delta mu, which is actually in a finite sample, it will be non-zero. It can't be zero. So what are the consequences of this being non-zero? Because you want to track the mean heights. So your sample itself has an error. Even if you forget that error, your noise adding mechanism added one more layer of error. So can one create? Yeah. What are the theoretical guarantees you can give for this noise adding mechanism? For example, there can be many variants of that. One version is this high probability bound that I mentioned, which translates that the mean of the uniform samples, finite number of them, should be less than or equal to some epsilon with high probability. Right? So that is an example of this type of. Okay. So the way to go about this is a concentration inequality, and there are other ways of doing it. Actually, this is one way. You can pose that as a concentration inequality question, and then keep trying to see if we can get this type of high probability bounds. So there are formal theoretical guarantees for noise hiding data mechanism one has designed. I took a very simple example of uniform, which I will take later also. Then yeah, others as well, and this is what it is. Is it clear? This is the way one can go about it. This is not the only question. There are many other questions one can ask, but this is one sample question or one typical question. And one way to go about it. Concentration inequalities may typically give you this type of high probability bounds. You can use in a certain other context, maybe the large deviations, and they will tell you something else if needed. Right. All right. Okay. What is the multi-agent RL that we are talking about? We are considering this is a framework for us, and is the number of agents. Careless is the state space. AI for each I is the index of agent, is the action spaces, and we are looking at actually a fixed finite horizon model right now, and we are trying to design a decentralized multi-agent RL algorithm for that, and along with a LDP, local differential privacy mechanism, and argue that what type of theoretical guarantees we can guarantee for our combination of decentralized algorithm with data protection mechanisms. Roughly, this is a finite horizon setup. So we can look into our so-called correctness of the algorithm by its regret, because it's a finite horizon thing, and we'll argue that there is a sublinear regret. We will consider 3-4 noise adding mechanisms, and for all of them, essentially we'll argue that there is sublinear regret, sublinearity in the number of episodes. That is one. That is a I think. Yeah, okay. So we are looking at this objective, the total expected total length of this entire set of agents, right? Where this R bar is actually the way we are doing this, it's sort of averaged across overall agents. This is the type of thing we are doing right now. There are other ways of doing multi-agent systems, but right now this is the way we are modeling. Any questions about this? This is the yeah.
It's not very clear what we mean by action with private information.
Oh, I see. Okay. Yeah, okay. I skipped this. I didn't see this right. I was in a hurry. Yeah, okay. This is good. This is good question. In the sense that it will allow what we are trying to aim is that actually what we are trying to design is what is called decentralized MARL algorithms. In a sense that in the morning, I think Dr. Jaykumar Subramanian mentioned about it. So I will skip some of those things. At a very, very high level, this multi-agent systems can be done in a centralized way or in a decentralized way. Roughly, not even decentralized way, centralized way versus. Let me rephrase this one. In a cooperative setup or a non-cooperative setup, the agents can be non-cooperative. Then one natural thing to ask there is that do the learning mechanisms in the non-cooperative setup learn a Nash equilibrium? In fact, there are counterexamples which may or may not be. Okay. So, in fact, last year I think there was a book by this Edinburgh person Stefan Albert which is on MARL, but that book takes the non-cooperative learning the non-cooperative equilibrium, Nash equilibrium. That's a setup it takes. One can do another version where you centralize in a certain sense. It is algorithm, you collect data and everything from each agent, and then your algorithm massages this entire data that is collected and then run about your RL tasks, which roughly means that actually you are doing single agent RL. There are challenges there. The communication overheads to be very heavy. And one of the aspects of this centralized modeling with a single agent is that intrinsically each agent will have enormous action spaces, and each of them and state spaces. Global model, MARL model will have a partition product of the large flows. So that is not very great at certain point of time. So the approach we are taking now is what is called a decentralized thing, in a sense that this framework is essentially due to a thesis of Tet and Zhang a few years back. In fact, I may mention that, and there are some reviews of survey papers by him and some other. I think he wrote the thesis with under direction of this game theorist Tamer Bashar. So this decentralized setup is the following that we are considering now. We say that the action of each agent is private information. It is not known to other agents. Immediate consequence is that the reward is typically private information of actions and the state. The state is globally known to everybody. So the reward is actually private information. So your algorithms, decentralized algorithms have factored in this aspect that we don't, other agents don't have the rewards of you in some sense. Remember that the task of the task we are looking at is has this R bar, which is the average of all such things. All right. What they pulled off in some sense is that they will parameterize the rewards and exchange the parameters only of the rewards. And still, their algorithms done in a certain other context like average cost and discounted cost, they will converge. They can show that. I will come to a bit quickly what is it's a simple observation, but has nice implications. All right, is this clear?
What's found out of the objective of the program? Are you considering how to train the agents on how to add noise to the data or something else?
No, there's something else. You are not training them. Our algorithm will make sure that it will be anonymized and still this objective function of the entire so-called team in a decentralized stage. So we are trying to train an optimal learning algorithms, RL algorithms in the multi-agent setup for this total cost problem, finite horizon, along with the data privacy incorporations, and argue that our algorithm will have some linearity.
So, and next question is, does this cost functions account for the data from previously?
Yeah, in a sense, for some of it I will address that. In a sense that we will compare with this, what is the B that you have issued with it and without data privacy and argue. But the C, the way we are talking about this R, I is a reward for agent I in an event period H. See, we are in a finite horizon, so even the non-stationarity of that will kick in and we have some consequences. All right, let me go. Okay, so these are one I didn't mention. I didn't write in detail here. So how does the agents as a whole will communicate? We'll assume that there is a what is called a communication network among themselves, and make simple assumption which they communicate eventually in some sense. That is, roughly speaking, we can I think we can keep using the word communication network or communication graph interchangeably. So the graph should be connected. Each node is an agent in this graph of communication where the agents are communicating among themselves. They may not be communicating in one hop, but eventually they should be able to communicate. So that along these, okay, I will come to it. So as I mentioned sometime back, the rewards will not be exchanged per se, only the parameters and versions of that will be exchanged, and they will exchange along this communication network or the communication graph. So agent I will communicate with agent J if it is connected, these parameters, direct connections in one hop. The requirement in this communication network would be they will eventually connect. But, I mean, otherwise we have disjoint things, and there are some works actually sufficient. I think Woman has some paper about these minimal conditions required about it. But we are not making any strong assumptions, we're just taking it weak ones and then go about it. All right. Yeah. So in that sense, our algorithm will be fully decentralized. It's not a single agent algorithm, but it's decentralized because agents need not declare their actions and hence their rewards. Roughly speaking, this community, by the way, there are two notions of privacy that are now floating around. I'm talking about two aspects simultaneously. This aspect is what is called what is the motivation for this type of rewards being withheld is what the originally said Katanjang and O is that is one aspect of privacy they mentioned. We don't want the agents to know or each agent to know other actions and other rewards. That's a privacy, in fact, the word they used it. We are talking about another level of privacy where the data entire thing after incorporating these reward parameters also not released publicly. The second part is via noise hiding mechanisms. Is this clear? The two aspects of this privacy that I am talking about. One due to the decentralization, and over and above, we want to add noise adding mechanisms, which for the entire data in some sense it will be anonymized. Am I clear? I hope I am clear. Any questions? Okay, this is a standard thing for these two factors because the finite horizon you can write like that. Yeah, and okay. So what a multi-agent LDP mechanism, we call it as epsilon delta is yielding or preserving epsilon delta or as guaranteeing epsilon delta NALDP if essentially this high probability bound holds for our algorithm. This is similar to nothing very drastically different from what I mentioned here. It's a high probability bound, the errors are low with high probability. So it is motivated by that section. That our mechanism should yield or should satisfy this for given epsilon delta, which are privacy parameters of the privacy parameters. This here. Any questions? So this community uses this word called user, the LDP community, DP community. Oh, I like okay. I mean, when I say DP community, it means differential privacy community, not the dynamic programming community. We have this DP word being popular in both sides. All right. The differential privacy community user says the word user, which in our case would be episode. And hence it is user is different from the agent I that you are talking about. Just want to make it clear because this community has this type of potentially confusing words. All right. Okay, they should differ only in one exactly one community, one component, and this original now they are indexed by agents. DI U for the episode in our case, which they call user. And this is before and this is after noise adding mechanism. Is clear? Am I clear? With this high probability should hold. Then if your noise adding mechanism can do this, then you say that it is epsilon delta LDP. That is one goal, so to speak. The other major goal is actually that our learning algorithms for the finite horizon should yield sublinear regret with this noise adding mechanism. So I think I wrote it. Yeah, okay. Let me write it. This is objective. These are regret. The first objective is that we should have sublinear regrets for our algorithm with noise adding mechanisms. So the question is what noise adding mechanism you want to use there, and that should yield a sublinear regret. There are other aspects to it. The front constants of the regret, sublinearity. To me, one of the major questions in this multi-agent systems is actually how does this is your objective to have a sublinear regret. I think many of you in other talks also it was mentioned. The regret should have sublinearity because in a sense to me it captures the learnability of the algorithm. In the context of MDPs or sequential decision making, a sublinear regret will mean that actually the algorithm is able to learn over a time so that it will have sublinear regrets. In the worst case, would have been linear, in which case you are actually equivalently your classifier in equivalent other contexts is doing a random guessing. A linear regret would have meant that. I believe this is the reason why they mentioned that sublinearity is a requirement for learnability of the algorithm. Okay. So okay. So now this is the first objective, and this is about decentralized. I will come to it maybe towards the end. One of the questions I feel in the multi-agent systems, and we'll comment on that in our aspect is that even though this is our main goal, objective one, it's an important question I feel in the multi-agent systems to see how your algorithms are actually scaling with the number of agents. I think that would be. I feel that is an important question, and we have something to say along those lines. I feel that would be an important question in the MAS multi-agent systems. That's not as the world, as I say, the world is getting more and more network, more and more agents interacting a lot, and we need to worry about what level the scalability with respect to the number of agents. You have a learning task that will have its own objective. For example, in horizon, maybe you are worried about a convergence of your algorithms and the rates of convergences. If it's a finite horizon, you may be worried about regrets, sublinearity regret, and how you scale with respect to the number of agents would be an interesting question. This is so we maintain actually our algorithm for which agent maintains a global value function. What is being subtracted is actually hypothetically assume that is full information. I mean, no privacy at all. That's the best it can do then. That is what our baseline and what we achieve here. That's the regret definition is between these. So in a sense, loosely speaking, our baseline is very, very demanding. Assume that it has full information. And that's what our benchmarking against, roughly speaking. Am I clear? Any questions? Okay. Yeah, roughly 15 more minutes. Yeah, at least. All right. Am I clear? All right. Okay. Yeah. Okay. So our framework allows, in principle, for any noise adding mechanism. We illustrated 4 different cases. One of them these are classical Gaussian noise adding mechanism, and one we call Laplacian adding mechanisms. These have the classically unbounded support, the entire real line. And we also consider the uniform one, which has a finite support, and we introduce what we call a bounded Laplace noise adding mechanism, which is basically a truncated version of Laplace random variable with a bounded support. The thing is that, yeah, okay, I think I mentioned all these things here. We quickly go to it. Yeah, okay. There is a motivation why we want to consider this uniform and bounded Laplace finite support. One simple way I can think about is that ultimately your machines on which you are implementing are actually have finite precisions. They are finite precision machines. So if your noise adding mechanism is also finite precision or bounded support, that will tally with it, that will gel with it. In other words, this Gaussian and Laplace unbounded support mechanisms will have, with low probability, of course, a large noise is being injected, of course, with low probability. So straight away, I want to take care of that with baking in the support of that into the noise adding mechanisms. Okay, that's the motivation for that. That's one motivation we want to consider. And we'll have some results along these lines. Roughly, the result would be our bounded Laplace mechanism. It has some tuning parameters, and if we not necessarily tuning parameters, it has some parameterized random variables, roughly speaking. And if you choose your endpoint of your bounded supports, we can achieve the regret on par, even better than the other supports. That is one of our observations. You choose your endpoints of your bounded supports carefully, so to speak, and it will be on par and sometimes better than the classical Laplace and Gaussians. That would be one of our results. Right. Okay. Yeah. So the other one, the sublinear regret is the main thing. As a MARL task, current horizon MARL task in the decentralized setup. The second one is that how does these two things, the regret and the privacy, trade off? That is what we would like to investigate with respect to different noise adding mechanisms. How do they trade it off? Yeah, I think roughly, I think it depends on the endpoints of that, and we can do better sometimes. All right. Okay, we are in the framework of this by now familiar functional approximations, which I think in the morning and many people have mentioned about it. The linear assumption that basically the dynamics are parameterized by linearly, essentially linear functional approximations, where the theta is the parameter our algorithm have to learn, and these fields in other language are what are called features. The user features on the context dependent features. So these are linear assumptions. Basically, we are doing linear functional approximations. And then we introduce in terms of this what is called essentially the cost to go PV. And then we can write that in terms of this, the theta and some other features. And yeah, okay. How does our algorithm learn these thetas? It is by basically ridge regression. We take a quadratic array and do a ridge regression. The ridge part of it, quote unquote, the ridge part of the objective function of the learning algorithm will handle the complexities associated with brittleities within it. Yeah, motivated by the classical classification learning theory and things like or regression theories. Okay. So yeah, then we argue that this part is due to the fact that the NMR setup we are doing is decentralized. The agent I, in particular, has a private action and a private reward, and they want to exchange parameters parameters of the reward, and that is what we do not by W's. So as I said earlier, there are two aspects to this privacy that you are talking about. One is due to decentralized stuff, and another is due to the noise adding mechanisms over and above that. What we are doing is first part over and above the standard stuff in the decentralized. I hope I'm clear. Any questions? Yeah.
The transition probability model, it's phi of S prime to an SA and then because
Yeah.
because is maybe search for an optimal.
Yeah, that is what, as I said, that is what we are going to learn. That's what our learning algorithm should learn.
What Wolfgang had shown yesterday, he had phi of S and some phi prime of S.
Yeah,
So that's a different.
I think that is a different. Yeah. Yeah, the Volcon setup is like it. We are basically parameterizing these three tuple, state action and next state. I mean, primarily by this phi of SCA in the linear setup. So yeah, we need to learn these thetas and hence we need to do these things. All right. Yeah, all right. We have to learn these thetas, fine. Our ML or algorithm should learn in decentralized way. We will essentially look at least square error and minimize that and do a bridge regression to that so that we add these complexity terms, which is basically now lambda norm W square, like the complexity of the learning class. It is a version of regression in the context of regressions. In fact, yeah, okay. Now this is a good question.
Like you have then there's fast-paying to the data and I do not know like what the motivation for fast-paying.
I mean, okay. So that's not the real motivation. Okay, it will come in two ways. One is that I will have two parameters to so-called learn. That will help me at one aspect. The other aspect is that the ridge will give you a quadratic term and optimization problem is well behaved because you have essentially a convex optimization problem. And you have scalable algorithms and global minimization, local minima. We piggyback on that type of activity. This regression, incidentally, in other contexts, I think, yeah, some of you are aware of it. It's popularly done about 30-50 years by Grace Waba, a statistician, who had a slightly different approach. He did the kernel learning, essentially in the regression setup. She had a different notation and different terminology. So, but very same as this type of stuff. Okay. Okay. Oh, so now let me tell you about essentially. Just give me a minute. This we are recall that we are doing a decentralized setup in the MARL where the agents doesn't want to declare their actions and the rewards. They want to parameterize the rewards and exchange them among the communication graph. So why that works in some sense is this. Suppose you parameterize the W, as I mentioned there in the earlier thing, this is something linear to the reward functions that you are doing, and this is something about noise sharing mechanics. So we in a setup, our algorithm have to learn the theta as well as W for different purposes. Theta and W for different purposes. The W is for maintaining the privacy of actions and rewards. The other is the algorithm should not declare the entire data for the that is the definition of privacy. So the first part comes from this simple looking nice idea. What they mentioned is that the risk minimizer of this reward function, because this R bar is your original thing and your parameter is R bar, which parameter is W. So look at the MSC basically and choose a W according to that. That's your goal. How do you choose your W is like this. Now, interestingly, a simple two, 3 lines of calculus will tell you that the stationary points of this or the global minima of this are exactly the same as this other optimization problem. Which is also the difference is you have a summation and that summation is over agent wise. And still convex quadratic and hence convex essentially. Right? So which essentially means that each agent can do actually the W on their own. They can learn and parameterize the rewards according to that and exchange according to that W. So this is a decentralized aspect. Am I clear? Any questions? They don't need to declare their rewards or exchange the rewards as it is. They can exchange only the Ws. They worked, and I think other aspects of Prashant thesis also worked on that. With respect to average cost type of ideas, we can show that this W exchanging W is good enough and still have convergent algorithms. That's a part of the second paper. Fully decentralized multi-agent learning with network agents. The networking is same as the communication graph or the network that I mentioned. In fact, there is a I believe 2-3 years back there is a survey by them of this type of aspects. This is the original paper. 10 minutes. Okay. Yeah. I will try to do that. Yeah, I should be able to. All right. Yeah. Each agent is taking independent actions. I think I'm just writing this again. The sensitive information is preserved by injecting noise. That's a goal of this work. All right. So if you do this with the modified Bellman equations with parameters of things, then convergence of these W's will mean that because they are continuous functions, that ultimately if the W's converge across episodes, then these Q's and the V's will also converge because they are continuous functions. So and hence essentially a result would be that as for all agents, the two factors will converge across episodes, and the value vectors will also converge across episodes. Our setup, because it's finite horizon, we work in episodes. The user and episode are from different communities. The RL community uses the word episode, which other community we realize it uses the word user. So information from the so-called server, that is algorithm, and that will update these data in this fashion. This has two factors on the right hand side, which will mean that if we can anonymize these two factors, which is a matrix and its inverse and a vector, if we anonymize them, our algorithm will be noise preserving. So we can devise a we can devise a noise mechanism involving bounded Laplace or a Gaussian and anonymize these two factors. Then the real information is not revealed or it is privatized. Am I clear? That motivates. See, one of the things I believe in this type of activity is to identify what part of the crucial, what part of the information, which is so-called crucial information, is to be anonymized. That will preserve the entire thing. So it will turn out because of this, according to me, because of this update, you need to just anonymize or add noise to these two fields, which is a matrix and a vector. That's what we'll do later. And it can be done by different noise adding mechanisms. And then the analysis, that's the design of the algorithm, so to speak. The analysis is that to show that with that noise adding mechanism, where the part of these two fellows will get indeed a subunit. That is analysis part of. Okay. All right. We are in a multi-agent setup. So what we do is actually is that we do a sort of really conservative idea. Each agent essentially takes a max-min setup. It feels that, remember that the entire team, so to speak, have one global what is that objective function, the learning algorithm. So each agent has to act locally. It will try to assume that the other agents are not doing very well. That's the main part. And still, knowing that or presuming or hypothesizing that they are not doing very well, it's minimum, they are doing minimum. So I will do the max. And then the entire algorithm should converge now. Am I clear what about it? We are doing essentially a worst case conservative type of approach. And max would be a very optimistic way of doing it. To contrast that. Yeah, I just repeated this. These are the things that will be. So okay. This has these two things. The one large matrix and the vector. So that motivated these. Ultimately, this theta hat comes from you do this with respect to this and this and this. So with respect to these updates, it will mean essentially that you have to update this outer product of these P's and a noise adding mechanism for these matrices, and for the other fellow we have to use a vector noise adding mechanism. That would be that. Is it clear? 5 more, yeah. All right, I will speed up. All right. So let me summarize the privacy guarantees. We can argue that the Gaussian mechanism or our algorithm MALDP is actually the Gaussian noise adding mechanism is epsilon delta private. For given epsilon delta, we can identify what are those matrices that are to be added. So the Laplace, it is with probability 1, it is epsilon error. For the other two, for the uniform, it is 0 error with high probability essentially. And for the bounded Laplace, it is epsilon tolerance with 1 probability. So that will be the privacy guarantees for all the 4. Which will essentially mean that entire spectrum of epsilon 0 to epsilon delta to 0 delta to epsilon 0, we are covering the entire spectrum. These 4 mechanisms are actually covering the entire spectrum in the epsilon delta space, so to speak. 0, either of them 0 or one of them could be epsilon and delta. Am I clear? Yeah. Okay. So this is, I think, yeah. Okay. So one of the we are not aiming for that. As I said in the beginning, our aim is to get sublinear regrets. Just because that I mentioned that it may be important question to ask in any multi-agent setup. How does your algorithms, which have another goal, sublinear regret type, are scaling with number of agents? We will argue that actually our algorithm scales with super linearly with the number of agents. For example, it's not quadratic. Remember that all agents can in principle communicate with any other body. So they are doing n square type of communications. It could have been quadratic. So yeah, some of you who are interested in further work or something like that, you can work on this type of problems, I believe. And there are some other things I may mention in a few minutes. I mean, can you scale much better than what you are doing with respect to the end? All right, this is a summary of that. The regrets will be in this way. So the final piece I want to say here is that this color, I think I wrote in maroon. Yeah, this is a function of the endpoints of the bounded Laplace thing. Assume that capital B is the endpoint of the bounded Laplace minus B to plus B and an epsilon. If you tuning this, you can get a scaling here. And yeah, okay. So this is a linearity with respect to the total. Okay, we are doing k episodes, and H is the capital H is a planning horizon, fixed planning horizon. So it's sublinear in this product. So hence essentially sublinear in the number of episodes capital because H is fixed at a constant. So yeah, so as I said, it scales super linearly with respect to the number of agents. 10 pi by 4, and yeah, essentially many times it's n by 5. I believe actually it can be further improved. I think it can do it, but we didn't do that. All right. Yeah. Okay. So what we can do is that we can show that if the epsilons errors are actually ordered in certain sense, the regrets would be ordered in other direction for both Gaussian and Laplace noise adding mechanisms. This is what I mentioned there. This the other, see, we are working with the, this is a privacy aspect of it. The utility aspect of this LDP thing we have done with respect to the performance measure being sublinear to the regret. How are you going to use this data? Yeah, we can learn up close to optimal policies for the multi-agent finite horizon thing, which is sublinear in the number of regrets. That's the earlier result. This result is talking about how good or how bad is your privacy aspects. Right. So yeah, and then the other one we are now this is for fixed Gaussian, we will have this, for fixed Laplace we will have this. Now this result talks about the comparative things about the Gaussian versus Laplace. So yeah, essentially for fixed epsilon, the Gaussians will have more regret. That's what we can show for fixed tolerances. And this is a bounded Laplace that I mentioned with minus b and plus b. So I will skip this. So we have a tuning parameter which is O of small b with respect to gamma, and the gamma is essentially less than 1. Then we can do actually much better, and it's comparable to the regret that is obtained by Gaussian mechanisms because except the front constants, the orders are same. So that is what I think roughly we summarize it here. All right. Yeah. Okay. So high probability, and yeah, I think in interest of time, I will skip this proof thing. Yeah, okay, I'll just summarize it. Yeah, okay, we have an informal statement where we have beta case that we are learning better, this beta thing. And yeah, okay, here is one example. Assume that these entire agents want to go from initial state to the goal state. They get this much rewards in this string, 0 in between. And yeah, this is how our regret profiles will look like. All are sublinear with the fixed Laplace with two different epsilons. You will have this blue and the yellow. This is consistent with the results that you got. This is the illustration of our results essentially. Yeah, and with respect to different ways of looking at the different epsilons for the Gaussian, this is how it looks like. This green and the red and the maroon, which is consistent with that. Okay. So I think I will sort of skip more or less. These are summary of our results. So essentially, we devised a generic one, then specialize it to 4 non-static mechanisms with 2 unbounded supports and 2 bounded supports, and argued for some nice peaking parameters with the bounded support. With machine precision being bounded, we can achieve what we can do with unbounded supports. Yeah. Okay, thank you.
So we do have about 5 minutes for questions,
Somehow managed within the time.
but he will be available.
Yeah, of course, yeah.
When this we extended to say stochastic program, those things that
Great question. So let me tell you a couple of things there. Without noise adding mechanisms, I think you may be aware of it. That is another chapter of Prashant's thesis. With the multi-agent stochastic shortest path, and hence it will have congestion now, because the classical stochastic shortest path is for single agent and have no notion of congestion. With this, okay, so we can argue that okay, our results are basically a sublinear regret with respect to the number of episodes there. Because I think you are asking, because it's a finite horizon model, you are asking that random horizon. Good question. So we argue that in another paper that we have sublinear regrets. We didn't do a noise adding mechanism to it. So in that sense, I think it is doable, but yeah, we didn't do that. Then the question, okay. So one more comment there is that our scaling with respect to number of agents, our goal is actually to sublinear regret, but still in that other work, it is superlinear, not quadratic with respect to number of agents. We are not aiming for that, but so happened. Incidentally, this would be the talk in a couple of hours from what Parimal is hosting on their platform. Yeah. Yeah. You wanted to say?
All right.
All right. Thank you. Thank you for patiently listening. And
We would like to thank the professor. This is a very timely topic. We're all dealing with data privacy issues. So putting that in the framework of oral is an extremely interesting area of research, and appreciate you coming out here and giving us this talk. So please do, talk to him further.
And yeah, thanks for kind words. And yeah, I wanted to mention in the beginning, but somehow forgot. Probably doesn't matter. Yeah, it is a tricky to have a talk on a technical topic after lunch. Yeah, I mean, I'm not looking for this long, but anyway, fine. I appreciate that you have the organizers will have their own concerns or constraints. I'm fine with it. So thanks for not. Actually, I don't know. Maybe many of you are just didn't like it, you didn't interact or ask any questions except 1 or 2. Maybe either you didn't like it or you have better things to do. Maybe you have taken a nap. But anyway, so thank you for patiently listening. Thank you. Thanks for your.
I'm sure they'll come and follow up with you. This is a very timely topic, but it is definitely interesting. I think, yeah, there's a bit of a lull after a heavy lunch.
That's okay. Yeah. All right. Thanks for trying this.
The next speaker we have is Professor Sandeep Janeja. Professor Sandeep is a senior researcher at the School of Technology and Computer Science at Tata Institute of Fundamental Research in Mumbai. His research interests lie in applied probability, including sequential learning, mathematical finance, Monte Carlo methods, and game theoretic analysis of cues. Lately, he's also been involved in epidemiological modeling, as well as in the use of machine learning techniques for monsoon weather modeling in India. So I will definitely have a question on that. He's currently the area director for editor for operations research and simulation and associate editor for stochastic systems. Earlier, he's also been on editorial boards of mathematics of operations research, management science, and ACM to Max. So a warm welcome to Professor Sandeep Juneja. Please give him a warm applause.
So I came here in 2015-16 and we had a similarly post-lunch session and we were all kind of exhausted because of lunch and all that. Santosh, my father was giving a talk. He told everybody to get up. Can you please get up? Please do, please do. You can maybe stretch yourself and take 3 rounds going. Just go 3 rounds.
Jogging. Editor job.
But this kind of, that's a good idea. Now you can sit down, now we can start. Place change.
This is not only in the beginning, I didn't have something.
Thank you so much. Okay, so I have given this, some related talk here about last summer. Well, how many of you were there in the audience? I'm hoping none. But, oh, wonderful. All new. Yeah. So good. So that's, no, it is actually, there are a lot of new parts to it, but I'll focus on best arm identification. So I'll tell you what that means, but this is all in a multi-arm bandit framework. So you have these slot machines, which are essentially bandits. They're referred to as bandits. So they all have one arm, and then you have multiple arms, and you have to pull the right one. So the best arm identification is that you're given all these arms. You want to pull them and find so you think of this as kind of having some probability of giving you a reward. This is having another probability of giving you a reward, so on and so forth. You want to identify the arm which has the largest payoff on average, right? Highest probability of reward, or highest expectation for generally. Okay, this is joint work with Agni Bandyopadhyay. But I'll also talk about average treatment effect, which says that, okay, now we don't just want to find which one is better than the other, but how much better. So much of what we do actually generalizes to that setting as well. So I'll give you a flavor of that towards the end of the talk. This is with my student Agni Bandyopadhyay and Shubhadra. She's a postdoc in Georgia Tech. Achal Basambhu and Vikas Deep are working with me on this KTE problem. So I'll talk about that as well. Okay, so the picture to keep in mind for all of you is you're given these 3 coins that you can flip again and again independently. This coin has a bias of 0.8, 0.6, 0.9. Now you don't know what the bias of these coins is, right? So you flip these coins and you have to learn which coin has the highest probability of heads. You have to learn this as quickly as possible. That's the game. So you'll stop at some point, you'll tell me, okay, this coin has the highest probability of heads. And I've given you already before the start of this that I'll allow you an error of 1%. So I've given you some delta. So you tell me I can give you a guarantee of 99% that this is the coin with the highest probability of heads. Right? And the point is how to think about this problem. What's the right framework so that one can come up with the best possible algorithm. Now, all of this, was studied in a certain manner. So how do I, whatever I do, in some sense, it's a very special instance of a reinforcement learning problem, which is one state, one time period. But what I'll talk about in this talk is this fluid-based method. So these are kind of new ideas which give insight on how to kind of view these problems. And I expect them to be extendable to general reinforcement learning problems. But that's a work for future. All right, so this is here. So we are, I'll give an intuitive overview of these problems. And then I'll say it's an optimal top 2 algorithm. I'll tell you what that means. This is kind of popular set of algorithms that are going around. But really what you should be doing here is changing the fluid limit. So I'll talk about what that means. Okay, everybody with me on what the problem is? I thought I'd make it more concrete for you. So this is 3 coins, heads, tails, 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 heads, tails, heads, heads, tails, heads, tails, heads, heads. Right? You get a reward, let's say when you see heads, you don't get a reward when you see tails. Which coin do you flip next? That's a decision you have to make. Which coin to flip next, and when are you 1 minus delta time short, then you can stop and announce which arm is the best. So that's the problem we're playing. No ambiguity, right? So whenever, I'll show you lots of terminology and you get bugged, but just remember we're solving this problem. And what we're really doing is, it looks like when this sequencing of coin flips goes around, it looks like this is the winner. But we just want to be very sure. We want to get enough evidence. There's a court of law that we want to persuade. All these guys are not the winners. So all the mathematics we are doing is basically gathering enough evidence so we can tell people that, okay, we are 1 minus delta short. Indeed, one of these coins is the winner, which looks to be the winner. What are the applications of this? So you can imagine this, all of this kind of comes, this kind of bandit world comes from clinical trials. So you have, for example, 4 vaccines, right? COVID time. You have to figure out which one works best, which one do you roll out. So you want to do this as quickly as possible. You want to do as little sampling as absolutely necessary. All right, placing advertisements on a Google search. Whenever you do a Google search, all these advertisements come up, right? So they're basically trying to understand which one has the highest probability of click from your side. So they're learning that from you. They're learning about you basically and trying to get you to click clicks. Web constructions among many options. Which one is most attractive to you? Recommendation systems. So movies to recommend. Again, they're trying to figure out your type. So which movie are you likely to like? Facebook posts to show, newspaper articles to bring to your attention, price to offer for a digital good, what's the right price for it? We're learning that. Travel route to recommend amongst many. So many applications, very simple problem with lots of applications which are widely used. As I have said many times before, much of what's wrong with the world we are in right now, the polarization that we see, these algorithms have an honorable role to play in arriving at that world. So it's important stuff. Okay, so this is interesting. This is an anecdote. So many of you play cricket or these kind of games, right? Imagine yourself being a selector. So you watch a person bat for a few times, few innings, and you decide, okay, this guy seems to be better than the others. We'll put him in the team. How many games should you see? So this says that to separate a probability of a coin with probability of heads 0.6 from a coin with probability of heads 0.4, you don't need 5 or 6 observations. If you want to be 95% sure, you need around 150 samples. So lots and lots of samples to separate two very reasonable things. This is kind of a fallacy of small data. We make conclusions often with very small data. So for students and for faculty right here, you need to get your paper rejected 150 times to be convinced that maybe it's not good draw. Otherwise, it may just be a bad draw. All right. Okay, so then I'll talk about this. Estimating a mean to a given specified epsilon accuracy with error probability less than or equal to delta. Right? So you say to yourself, I want to find the mean, I want to come up with a confidence interval. Confidence interval should be of epsilon width. I specify that this much error I'm willing to live with. And you give me this confidence interval, which is correct, which is likely to contain the mean with probability 1 minus delta. So the ideas that I discuss here also apply to that setting. So we come up with the best confidence interval in specific sense. Okay, coming back to best arm selection. So you're with me on this, right? We are given k unknown probability distributions. So coin flips are example, Bernoulli outputs are example of outputs from probability distribution. So we are given k probability distributions which are not known, we don't know them, but we can sample from them. And we want to find the distribution which has the largest mean using the fewest samples to generate, while keeping the probability of false selection to less than or equal to delta. So problem is clear? All right, so let's carry on. So first I'll just show you some popular algorithms. It's good to see them. It's very elegant kind of mathematics, but it's very simple. Okay, so our friend Hobding. When you're young, you have real friends. At our age, you need these folks, some guys who help you a lot, they become your friends. Hobding is something that's xi lies between -1 and 1, independent, identically distributed with zero mean, right? So law of large number central limit theorem, everybody knows that in this room, right? The sample average converges to 0, right? Central limit theorem tells you the deviations of the order of 1 by root n. So if you're in computer science and you're publishing in top conferences, okay, that's the norm, no big deal, you're expected to do that. If a student gets a best paper award in stock, okay, that's in the center limit theorem regime. But our interest is in large deviations. So Hoppening inequality helps us with large deviations. This sample average, which is converging to zero, what's the chance that it's actually greater than equal to a specified epsilon positive? So that's going to decay exponentially in n. You've seen this before, right? Most of you seen Hoppenings in this. And what's nice, charming about this is it's a uniform bound. It's for all random variables which lie between -1 and 1. So it's a nice bound. So this is large deviation, and analogy here is, okay, in next 1 year, professor from IISc or from TIFR gets a Nobel Prize. That's a large deviation event. Please. Okay, so what do we gain from this Hoppening inequalities? What we get is something like this. So I wonder if I've given the to write that. So basically what I can do is, yes, I'm missing a slide, but what I would have done was I would have just used kind of, I would have asked myself, what's the probability that there exists an n so that the sample average exceeds some term here which is decreasing with n. So I create this tube and I say, when there's a sample average after 5 samples, or sample average after 10 samples or 15 samples, what's the chance that it remains in this tube? And that probability, so x bar t, remains between mu plus minus alpha t with probability 1 minus delta. So these tubes I can construct just by Hoppening's inequality. Is this clear to everybody that I can do this? And how do I construct this tube? So I missed the slide, but if I take, for example, alpha t to be something like this, log of 1 by delta by t, square root of that, something of this formula. Let's take this exactly this formula. So if I take alpha t in this manner, this is t here. As I said, there exists a t where I see this large deviation. I can upper bound that by summation over all t, and I get that that's going to be less than equal to delta. So probability that the sample average ever deviates outside this tube, I can bound by delta probability. That's the message I want to take from here. So that can be done. What's nice is that all the rogue parts which make analysis life difficult, that's outside the tube. Right? So I don't have to worry about them now. Within the tube, my analysis is much, much simpler. These tubes are just chosen very well. So how are these tubes chosen? Again, think of alpha t as square root of 4 times log. K is the number of arms, kt upon delta divided by 2. So if I choose my alpha t in this manner, probability of each arm taking a large deviation outside that tube is bounded by delta by k. Probability of any arm misbehaving is bounded by delta. That's when the state of it. Okay, so now that we know this very nice algorithm from 2006, Dar, Manor, and Mansoor, successive rejection algorithm for arm revolves in 0 to 1. So I sample each arm once, right? If at sample T, I look at the current winner, x bar max T. That's the current winner. If any arm loses to it, and what does losing mean? If the difference in the sample average is more than 2 alpha T, then I simply throw away that arm. That arm is rejected. So the algorithm is very simple. At any stage, there are some active arms which are still in play. So I give them all one more sample. I compute their sample averages, and I see if some arm is lost in this battle. The difference is more than 2 alpha T. Then I throw away that arm. All those arms I throw away, and I carry on like this. And whatever remains in the end is the winner. Yeah?
Just to understand the notation, what is x bar? X j bar t is the average of pulling returns by pulling arm j.
That's good. That's good. Yeah.
And what is this x bar max?
This is just the arm which has the largest sample average. Yeah. So thanks. So I look at all these number of arms which are still active. I find the sample averages. This is the sample average of the arm with the highest sample average. And if some j arm is deviates by more than 2 alpha t is something well known. It's very clear. It's a deterministic quantity. So if you are bigger than 2 alpha t, then you lost. I throw you away. Is this clear? Yeah. And repeat till one arm left. When one arm is left, that's the winner. So algorithm is clear, right? So why does this work? Very simple. The point is, whatever happens outside the tubes, I don't care. You gave me delta error probability, that's absorbed in the delta probability. Within the tubes, I can give you the guarantee that I'll find the best arm. In other words, within the tube, suppose I have two arms. This is mu1 best, suppose the arm 1 is the best one. Its sample average will lie in this tube with the probability it is 1 minus delta by 2. Second arm sample average will lie in this tube. My claim is, if you just look at these good set, you'll never throw out the best arm on this good set. Why? Because x bar 1t on this good set is always bigger than mu1 minus alpha t by design, right? X bar 2t in this case is x bar 80, I'm calling it, but x bar 80 is less than mu a plus alpha t. Now, when will I throw this guy? When this arm loses to the second arm. So when x bar 80 minus x bar 1t becomes better than 2 alpha t. But that won't happen. If you just see the calculations here, it's always going to be less than equal to 2 alpha t minus something positive. I'm assuming that I have a unique best arm. So this is bigger than this. So is this clear to everybody? That in this world, I will never throw away the best arm. Right? With probability delta, anything can happen, I don't care. But with probability 1 minus delta, I'm not going to throw away the best arm. And if I just expand my cubes to not be like a mu plus minus alpha t, but now I'll make them to be plus minus 2 alpha t. Right? Then, eventually you can see that on my earlier cube, x bar could have gone down as much as mu1 minus alpha t. So x bar minus alpha t, is this curve right here, is going to be at least as much as this. And for the second arm, it'll be at most as much as this. So when they intersect, at this point, I would definitely have stopped. At this point, I would definitely have thrown away the second arm. Because at this point, x bar 2t plus alpha t will be less than x bar 1t minus alpha t. So I can calculate this point, and this gives me a bound on sample complexity. It tells me that I need order log 1 by delta samples, and this term here, which is mu max minus mu h squared. So you get these kind of terms. You get the idea, right? How one will prove these things. So I'm just identifying a point on a good set where I must have stopped. Again, bad set doesn't matter. So it's a very clean way of thinking. You isolate things, good set, bad set, everything comes out nicely. Okay, so this was kind of a simple example. Now I'll give you a way of kind of, these are all problems of testing of hypothesis. You have a hypothesis and you look at the data that this arm looks like it's the best one. You want enough evidence so that you can control your type 1, type 2 errors. That's the old statistic way of thinking about it. But I'll just give you my view on how to think about these things in this setting. So lower bounds and algorithms that match even the constant in the lower bounds. Right? So we'll develop a lower bound. These many samples you have to give to each arm. Basically, you are gathering evidence to say that, okay, arms which look suboptimal are indeed suboptimal, but you want to be delta probability sure. So you gather evidence and you have enough of it. So that will give us a lower bound. How much evidence do we need? And then we develop algorithms which exactly match the lower bound. And then we'll develop much better algorithms which exactly match. That's the whole spirit of this. Okay, so trivial lower bound. So suppose each arm is given log 1 by delta to the power alpha sample. So think of this as square root of log 1 by delta sample. The claim I want to make is if you just give square root of log 1 by delta samples to each arm, that's never going to be enough. That will not ensure that you have delta accuracy, delta error. Why is that? Because again, go back to large deviations. X bar n equivalent to A, probability of this. Large deviation tells you that that's just exponential of negative n times some function of A. For those of you who know large deviation, those who don't, just know that these probabilities are exponentially decaying in the number of samples n, as you saw from Hawkins inequality. Now plug in n equal to log 1 by delta over alpha. Just plug that in here, and what you see is that you get a term here, which is going to be greater than delta as delta goes to 0. Because the I is a sum constant, and then I have delta raised to power IA divided by log 1 by delta over 1 minus alpha. This quantity together, for as delta becomes small, will be greater than. So basically, you've not given enough samples. Your sample averages can take any value whatsoever with these many samples, and you can't control the probability to be less than delta. Probability of error to be less than delta. So this is a trivial lower bound that at least you need log 1 by delta samples, right? But we want to come up with a much more precise lower bound. So we'll go in that direction. What I need for that is Sarnoff's theorem. How many of you know what a Sarnoff's theorem is here? Just raise your hands. You know large deviations, but you don't know Sarnoff's theorem. Okay. So good times. We're going to learn something today. So green is the true distribution mu, let's say. So I'm going to sample from a probability distribution which has support on 4 points: x1, x2, x3, x4. Right? And two probabilities are these green probabilities. Right? Now I generate a lot of independent samples from this distribution. I collect those samples and I create an empirical distribution, right? A histogram. And suppose that is there. Now, intuitively, we know from law of large numbers that this red bars should be very close to the green bars, right? When the number of samples become large. Sarnoff's theorem tells us if they are not, what's the probability that they are not? So suppose empirical two distributions mu, and my data looks like it has a distribution mu. What's the chance of that happening? So it's exponential of minus n to the ladder of between mu and mu. To that ladder, everybody knows here. That's just this quantity right here. Mu I log of mu I upon mu I. Way to think about this is mu is a true distribution. Mu is what it looks like. So this is going to decay exponentially. So this is like the bird's view, as per our yesterday's talk. If you were to do the frog's view, you put in all the polynomial constants here. It's enormously messy in general state spaces. Because whatever I'm telling you in this 4-point support distribution also holds in Polish spaces, and then these things are still true, but then all this is quite messy. But nonetheless, this is very nice and clean. So is this clear? Everybody with me on this? If mu is a true distribution, I see a lot of data. The data looks like it's following mu distribution, then this is the probability of that happening. That's all I want you to carry for the next slide. Right? So let's go with this. Okay, then what's going on? So I observe samples. So I'll give you a heuristic argument for the lower bound. Two arms, two probability distributions. I observe samples N1 and N2. N1 samples from first distribution, N2 samples from second distribution. The empirical distributions look like mu hat 1 N1 and mu hat 2 N2. Right? These are two empirical distributions. Now, I'm going to idealize the argument a little bit. So with high probability, each empirical distribution looks like the true distribution mu I. With high probability, that's going to be true. Sarnoff's theorem. So now that would suggest that if indeed the mean of first sample average is bigger than the sample in the second arm, then it must be true that the mean of the first arm is better than the mean of the second arm. Right? That must be true. But I need enough evidence to be sure. So as a skeptical scientist, you wonder that all these distributions that I'm seeing are actually a result of large deviations that the data has conducted. It looks like first arm has mean 5, second arm has mean 3. But maybe the truth is something else. Maybe the true means was 4 and 4. 4 for this guy, 4.1 for this guy. And they just took a large deviation and it looks like they're 5 and 3. So I want to rule out that possibility, right? I want to rule out all the possibilities where the mean could have been in the opposite order. So let's look at that possibility. So I want to rule out the possibility, that the true distributions are mu1 and mu2, where m of mu1 is actually less than m of mu2. So that I want to rule out. So what is this? And so I look at all the set which makes alternative conclusions, mu1, mu2 such that n mu1 is less than n mu2. For any such set, the chance of seeing, if the true distribution mu1 and I'm seeing mu hat 1 in n1 sample, roughly the probability looks like this from Sarnoff's theorem. Similarly, for the second distribution, these are all independent samples, n2 samples, mu hat and mu2. So I look at this, my best guess for this probability. I look at it in worst case. Amongst all the alternative distributions, all the alternative distributions which are alternative conclusions, which one is most likely to confuse me? So I identify that, and that probability I want to keep less than 10. Right? So that, and I idealize this, so I replace mu hat 1 and mu hat 2 with mu1 and mu2, true distributions. So I just choose, I just want to keep this probability here, less than equal to delta, and that's going to give me a lower bound on n1 and n2. So that's a very heuristic, hand-wavy argument. It's persuasive. I'll just talk more about this, as, how to make this persuasion more tight. But let's just see this now for k arms. So this is all probability distribution of the k arms, mu1 to mu k, such that m of mu1 is less than some other distribution. Actual data may again look like arm 1 has the largest mean, But these are the distributions that I'm worried about. It could have been any of these distributions. Data could have been coming from here, and I'm drawing a wrong conclusion. I want to make sure I have enough evidence to rule all these out. Right? Again, back to the coin situation. It looks like first coin has the largest probability of heads. I just want enough evidence from other coins so that I'm convinced that the chance that they actually have the largest probability of heads is less than delta. Okay, so in this case, I'm trying to bound this probability. This was the same argument that I gave you. I want this to be less than equal to delta. So everybody with me on this? Okay, so what does this give me? This gives me this problem basically, that this quantity right here, all the mu where I make the wrong conclusion, this term right here must be greater than equal to log 1 by delta. And so I want to choose my NAs which satisfy this constraint. This gives me enough evidence. If I have these many NAs, then I have enough evidence to be convinced that, okay, I'm making the right conclusion. And I choose my NAs to minimize this, because I want to minimize samples I generate. So this is the lower bound optimization problem that I come up with. It's a nice optimization problem just from these things. Now, for some of you who are wondering, okay, this is all very hand-wavy, where's the mathematics behind this? The mathematics comes from the data processing inequality. How many of you have heard of data processing inequality? It's a very PCE thing. Oh, good. A lot of you have actually heard this. So, you know, X is a random element. For us, it's when I sample all these things and I observe all these samples up to a stopping time. That's my random element. So X under one probability distribution, X under another probability distribution, Kullback ladder between them dominates the Kullback ladder between G of X under that probability distribution P and G of X under probability distribution Q. So when there's information loss, Kullback ladder distance shrinks. So everyone kind of intuitively can see what's going on here, right? You don't have to go too much into this. So now in our case, you know, I'm giving you all these, there's a mu probability measure and there's a new probability measure. See, they are differing in the distributions that generate samples, flipping coins. You know, one is flipping coin with probability of heads 0.9, other with probability 0.8. But for a given data, the conditional probability of evolutions are same under the two. Because my algorithm just looks at the data and decides how to move. So those are same. So all that shows up when I look at this Kullback ladder is the distributions that they give to each sample. So with this, you know, I'm going to look at, you know, the Kullback ladder between this whole random element which I mentioned to you. And here I'm just going to look at indicator function. So this is the indicator function of the event under mu. I chose the wrong arm. Under mu, I chose the right arm. Right? IE is the event that, although the true distribution was mu, I actually said mu was not the true distribution. Mu was not the best arm. And mu is the event that some other arm was the best arm. So by choosing these things, I can actually show this is a calculation that this will look like log 1 by delta. And this quantity here, you can simplify it. It's not at all difficult calculation to come up with this. Expected number of times arm A will be pulled under true measure mu and Kullback ladder between mu and mu. So this is exactly going to be the right inequality which I just showed you there. Now I have expectation here, which I get from, you know, by evaluating this quantity here, and this is going to be getting into log 1 by delta. So I get same thing here. And these expectations, I just replace them with NAs and choose the smallest NAs which satisfy this. So that gives me a lower bound on these expectations. So that's the way to make this precise. So data processing inequality is the kind of secret sauce which makes the lower bounds work. But the Sarnoff's theorem way of looking at things is just makes it very intuitive. You have an intuition for exactly what's going on. Okay, so now, so let me just, you know, for a few of you who have not walked out so far, let me just summarize the whole situation for you. So where are we? I never do this, but I always say to myself that I should do this. So we are given number of arms, 3 probability distributions. We can sample from them, and we want to find the arm with the highest probability of heads in this case, or in general setting, highest expected value of rewards. So that's the game, and we want to do this as quickly as possible, right? And then we said that, okay, what we want is basically, you know, we allow the probability of error of delta. So what we did was this heuristic argument, right? Like, how do we decide that the number of samples that we've given to suboptimal arms is enough. And the logic is that if I've given you N1 samples to arm 1 and N2 samples to arm 2, and I've observed these distributions, very likely these are close to true distributions. So if I'm idealizing things, I'll assume that these are true distributions. And so it looks like the arm which has the highest mean must be the arm which actually is the best arm. But as a skeptical scientist, I'm concerned about all the alternative distributions which could have given me these distributions here. Right? So I want to rule them out basically. So what do? I look at this alternate distribution mu1 and mu2, where the conclusion would have been different. mu1 is less than mu2. Under mu, the true distribution, mu1 is bigger than mu2. In this case, it's the opposite. So I just want to rule out these options. Right? So what's the probability that the true distribution mu1, but it looks like mu1, if I give N1 sample? That's roughly given by this term right here, by Salo's theorem. Probability that the true distribution of second arm is mu2, but it looks like mu2 with N2 samples. That looks like this quantity right here. So this, and you know, mu hat 1, mu hat 2, I can approximate them by the true distribution mu and mu2. So this is the probability that I want to, I want to control. This is what's worrying me, which is what I want to guard against. So I look at the worst case probability amongst all mu and mu2 in this set, all the things which can confuse me, and I keep that to be less than or equal to delta. This is less than or equal to delta. Now I just take log on both sides, right? And I get this problem. So okay, same thing for k arms. So I get this probability. I want to keep this less than or equal to delta. So basically, I get that this quantity right here should be greater equal to log 1 by delta. And now I choose my NA. I choose to minimize this while holding its constraint. That's how I get control of. And I can justify all of this using data processing. So that's all we've gone so far. This is just giving me enough evidence so I can rule out that other arms can't be the best ones. All right, so now let's move forward. So I'm looking at this optimization problem, right? Minimize this. Now I break these constraints up into, k minus 1 separate constraints, each for each suboptimal arm. So this is the set where mu such that best arm is mean of the best arm is dominated by mean of the 8th arm. Right? Because I can write this set where I make alternative conclusions as a union of sets where the best arm loses to arm A for all arm A. So I write this as a union, and then I can separately write these constraints for each one of them. So it has to be true for each one of them. So I write it separately for each one of them. Now in this case, now I'm basically seeing all the news where arm 1 gets confused with arm A. True distribution was arm A has a larger mean, but my data are saying that arm 1 has a larger mean. So where will I get confused? I have to find this minimum here. Turns out that the most confusing distribution is at this point, x1a. It's a convex weighted combination of the two means mu1 and mu8. So basically, the data says arm 1 looks like it's coming from mu1. Arm A looks like it's coming from mu8. What's the most confusing distribution? It's at the point where the means are basically equal at this point. So if their means were basically equal, arm A was just slightly more than arm 1, and they took a large deviation, then this is the exponent I'll get of the large deviation. So I want to make that to be less than delta, so I get this quantity right here. Is this clear? What I've done is, very quickly, I'm looking now at all distributions restricted to single parameter exponential family. Just to keep the notation simple, I'm not talking about the whole distribution now. I've restricted myself to say Bernoulli distribution, where there's a single parameter which explains the distribution. Normal distribution with variance fixed, single parameter which explains the distribution. So it's a large class of distributions. How they help me is I don't have to worry about the whole distribution now. I just worry about single parameter. Notationally, my life becomes much simpler. So now, that's why I can talk about x1a being 1 point. This is actually a distribution, but just 1 point whose mean is equal to this quantity. So if the true distribution for both the arms was around here, and arm A was slightly higher than arm 1, then that would make what I see most likely amongst the set of all ordinary distributions. So that's how I get this constraint. So now with this constraint for each A, I want to minimize this quantity right here. That's my optimization problem that I want to solve. So the point is this: I have a crisp and simple lower bound problem. Now I move on to designing an algorithm. Now, one algorithm is very commonsensical. What I'll do is I'll generate some samples of all the arms. I'll estimate mu1 and mu8 for each arm. I'll empirically estimate what the means look like. I plug them in here and I solve this optimization problem. Right? And the optimization is the problem will tell me, okay, what should N1 be, what should N2 be, what should N3 be? Now I know that I don't really know these news very well. With high probability, I have a pretty good idea, but still I can be wrong. So I don't trust the solution of the optimization problem so much. But I do use it as a guide. I go a little bit in that direction. Right? I get more data. With that, I update my new ones and new ways with this more data, and I repeat this process. And I keep on repeating this process until I'm convinced that I have enough evidence that I'm delta sure, 1 minus delta sure, that I've got the right answer. Okay, so this is kind of clear. So how do I become 1 minus delta sure? Extremely elegant theory. All of this work actually goes back to Wall's sequential analysis and Chernov's famous paper in 1959 on design of experiments. But he introduced this idea that you look at, you've seen this data and you ask yourself which parameters best explain this data, which maximize the likelihood of seeing this data. It's a nice optimization problem. That becomes the numerator. And denominator now becomes, okay, under the alternative hypothesis, what's the likelihood of seeing this data? And in the alternative hypothesis, let me take the worst case. So let me take the maximum here, which makes the likelihood of seeing the data most likely under the alternative hypothesis. This ratio, if I take the log of this, log doesn't matter, I exactly recover the quantity that I've been taking so far. Now, this was exactly the quantity that we saw in the lower one. We wanted this to be greater than log 1 by delta. Right? Except I have mu here. So this ratio is exactly this quantity. I look at it over all mu in the alternative set. I don't know what the alternative set is, but what looks to be the alternative set. There's a set, there's the arm which looks to be the best one. So all the collection of means, we have a different conclusion that comes here. So if this quantity becomes large enough, essentially log 1 by delta plus some small order terms, that's when I stop. So it's also very intuitive. It's suggested by the lower bound that if mu hat is very close to mu, and if I stop at this time, I'll exactly be matching my lower bound. So it's very, it has a lot of kind of intuitive flavor to it. That this is what people do. This is called plug-in algorithms. They tend to be slow because they have to solve a lot of optimization problems during this process. So then a lot of people were proposing these top 2 algorithms, which I'll explain to you now what this very, kind of very beautiful algorithms. And so then the question, but they were not doing it optimally. So the issue was what's really going on, how do we understand this? That's where this talk is going right now. So top 2 beta optimal algorithms were being discussed. 2016, Dan Russo took lead in this. And then there are a lot of other papers, but this is a paper which came out recently for influential. So let index IA be the empirical version of this quantity right here. Recall this is the quantity that has to be bigger than log 1 by A, log 1 by delta. Basically, this is a measure of how likely arm A is to be the true one, although arm 1 looks like it's the true one. So smaller this index, the better it is. You want it to be bigger than log 1 by delta, then you're convinced, okay, arm A is not going to make it. This is the evidence you need to convince yourself of that. But smaller this is, the most likely that arm is to be the alternative. So please don't starve any arm. General advice for everybody, it's a good practice, arm or anything, don't starve. But what this means is that make sure that you don't give very few samples to any one arm because then you can't draw any conclusion. So if totally you've given n samples so far in your sequential strategy, make sure at least root n is given to every arm. Then you won't draw conclusions. Select arm with the largest sample mean with probability beta. That's a winner arm, empirical winner. Select challenger arms. That's why top 2. You pick up the empirical best and the challenger arm. How do you decide the challenger arm? The one with the smallest index. So then you pick up these top 2 arms. With probability beta, you give a sample to the best arm. With probability 1 minus beta, you give a sample to the challenger arm, and that's how the algorithm proceeds.
What is the index? It's the empirical version of that.
Empirical version of this, yes. Yeah, just mu hats here. X1 is, it's good to see, X1A is this quantity, N1, so mu hat 1 plus NA mu hat A. All right, so this is it. And when do you stop? Again, when all the indexes are bigger than log 1 by delta plus smaller order terms. Just the kind of stuff I've been showing you, it's exactly this. You've got enough evidence that you can rule out each arm being a winner. That's when it stops. Right, so that's the algorithm. The only problem is one doesn't really know what the optimal beta is. So this algorithm is shown to be beta optimal. If you restrict the best arm to get beta percentage of samples, amongst all those diagrams, this will perform match the best one. But what's really going on is it's interesting. See, whenever you see some arm which looks very likely, when you with 1 minus beta probability, this is a challenger arm. You give it one more sample. So in some sense, you increase the value of index. You build more certainty on the fact that it's a suboptimal arm, right? Because this increases. So this index increases. It catches up with some other index, which was larger than this. Now you're uncertain between these two arms, both of them give. So next time around, you pick, they fluctuate a little bit, so you pick up whichever ones are smaller, but you keep on giving them samples, they move together, then they come together with the third most likely arm. Then again, you give them samples, they come together. So really, this is what's going on. There's kind of like a water filling kind of algorithm that's going on here. So how do we formalize it? That's why we're going with this. So basically, you see all of this. The picture always becomes clear when you see in the right limit. So we'll see this picture in the asymptotic limit where these things will move exactly together. So that's where we'll find the fluid behavior in this. So again, the optimization problem is minimize summation NA subject to these constraints, K minus 1 constraints, right? Now you can actually show that this will have a unique optimal solution. So now we are trying to improve on this beta probability which I told you, where these are exactly going to be tight, and this sum ratio term is going to be equal to 1. So this quantity suddenly shows up. But it's again very intuitive stuff. So if I'm solving this optimization problem, if I keep my NA to be 0, my X1A also becomes equal to mu1, and this whole quantity becomes 0. Similarly, if I take N1 to be 0, my X1A becomes mu A, and this whole quantity becomes 0. Meaning, if I'm going to solve this problem, all my allocations have to be positive strictly. If they're strictly positive, then this constraint has to be tight. Right, so this is no surprise that at the optimal point, you will get this equality here. Yeah.
So the question is, why do this not as kind of stop?
So stack and stop is what people usually do, and this turns out to be because stack and stop solving optimization problem repeatedly. You solve an optimization. This is an efficient alternative where you don't have to solve an optimization problem.
Still achieves asymptotic.
Still achieves and empirically much better. Yeah, empirically much better than time. Sample complexity wise as well as computationally. Yeah, so both ways. And presumably, hopefully, this generalizes to reinforcement learning problems. That's where I'm going with all this. Okay, so now we got that this is tight. This constraint is interesting actually, because if I make this tight, I can always perturb N1 by delta and change my NA in such a way that this equality is maintained. Right? So if I do that, I should not be able to improve. So for that, I need this to be exactly equal. If it's not equal, then one way or the other, I can improve in one direction or the other direction. Who any other question?
You said you're going to go towards this fluid defect type.
Yeah.
I wanted to know, when you say asymptotic, do you mean the number of samples go to infinity or the number of arms go to?
No, samples. Arms is going to be fixed. Arms going. So this you can see, right? Because I can perturb these back, maintain equality, and that gain should not lead to any improvement. Otherwise, I will not be at the optimal point. Then I'll be improving. So if I'm at the optimal point and this equality must be true, then that gain will not help me in either direction. That's why equality. So good to know these things. Now this automatically suggests an algorithm. So this is optimal to talk to algorithm that we propose. So let G denote this ratio sum. IA empirical version of this ratio sum. We just know the empirics in the algorithm. And IA is again the empirical version of these indexes. So again, please don't starve any arm. Actually, when you run the algorithm, starvation doesn't happen automatically. It's a good economy. Everyone's doing well. You don't have to worry about it. But in any case, if G is greater than 1, then sample arm 1. You can actually prove that this ratio sum is the monotone function of N1. So it's going to decrease if you sample arm 1. Ideally, it will decrease. In noisy world, it will decrease on average. If G is less than 1, sample arm with the empirical smallest index IA. Again, ideally, this will increase this guy, and noisy world will increase on average. So, we replace beta probability just by these two steps. When G is greater than 1, sample the empirical best arm. When G is less than 1, sample the challenger arm. And then again, you stop when you have enough evidence to stop. That's same as before. So why does all this work, and how do we understand and appreciate this? And this is where I hope that all of this generalizes. But after enough samples, the algorithm closely tracks the fluid paths. So what's the fluid path here? We again create an idealized version of this situation. What's the idealized version? Empirical distributions are equal to mu, the true distribution. Right? Once G is equal to 1, it stays 1. I told you this ratio sum. When G is greater than 1, you sample N1, it brings it down. When G is less than 1, you sample a suboptimal it brings it up. So it fluctuates around 1. You can prove that those fluctuations get tinier and tinier. So in the ideal version, this remains equal to 1. And once two indexes become equal, so I'm giving sample to these suboptimal indexes. Once they become equal, in the ideal world, they're going to just remain as an equality. So they'll move together. In the actual world, they fluctuate and move together. So this is an idealization. Now I can actually identify the fluid limit. With these constraints, I get a bunch of equations. I find that the Jacobian of these equations with respect to the allocations NAs is actually invertible. So then I can actually do, that tells me that I can apply implicit function theorem to this. These NAs, the allocations are going to be unique function of total number of samples. And there'll be nice differentiable functions of these. I can differentiate and find the ODEs that these allocations are going to satisfy. So I'll actually be able to find those ODEs and then I'll track those ODEs. So it's like in stochastic approximation theory. You have a stochastic approximation recursion. After a while, you argue that they're actually very close to an ODE. So you show that you're tracking the ODE. So same thing here, except that the ODE actually comes through via this implicit function theorem. Okay, so what's going on here? Fluid view. So suppose after initial exploration, my G is greater than 1. Then my algorithm will keep on giving samples to arm1 and make this equal to 1. This is the idealized world where this will actually be a monotone function and once it come down and become equal to 1. At that time, suppose my one index is at this level, other index is higher, third index is yet higher, so on and so forth. Then my algorithm will give samples to arm1 as well as this guy. Arm1 as well as this guy. What's going to happen is to feed arm1 and minimum index while maintaining this is equal to 1. So what will happen is that the smallest indexes are going to increase at least linearly. That one can prove. That they're increasing at least at linear rate. While the larger ones are not being pulled right now. But they have this N1 component in them. So they do rise, they do increase when I pull the arm1. But they will increase sublinearly. So eventually this guy will catch up with this guy. Then these two will again move linearly. This will move sublinearly. This will catch up with this guy. So on and so forth. Once all the arms have caught up, they're all equal, and G is equal to 1, I actually am at the optimal point, barring the fact that my index is not equal to log 1 by delta. They're equal to each other, but they're not equal to log 1 by delta. So then I just keep on giving them samples until they become equal to log 1 by delta. And that's where I stop. So I reach stability, I just chase them now. I'm choosing at the right kind of samples to all of them, and that's how everything works out. So that's the flavor of things. So key step in analysis is the implicit function theorem. It shows that the fluid solution satisfies ODEs concatenated together. So whenever I have some small set of indexes which are together and small, and I have G equal to 1, I give them samples, these small set of indexes will rise and meet another index. Once they meet, then my ODE is going to change. Then all these four are going to be together. So then they'll go together. So I have to concatenate these ODEs basically together. And my algorithm is going to be changing these ODEs concatenated basically. The algorithm after sufficient large samples closely tracks the fluid path. So that's a really hard part to prove. I could have said these things 8 months ago. I used to, this picture was there, but proving took a very long time. So again, so implicit function theorem because Jacobian of, so I look at this constraint here. I look at these constraints, and B is a set of indexes which are small. All the indexes are equal and small. And I look at this constraint, N1 plus summation NA, and these are NA and B complement. These are indexes that are not going to touch. So my variables are these NAs and N1 here. And I have the right number of constraints. N is my total number of samples. So implicit function tells me that once you give me N, the total number of samples, I get a unique solution to N1 and NA. Basically, you tell me I give total these many samples to system. If these equations are true, it tells me how many samples have gone to best arm, how many samples have gone to each of the arms A. And now I can differentiate and actually find the ODs satisfied by these N's. So I differentiate them. So D and B by Dn is called N prime B. So I get these. N1 prime B is given by this expression. N prime B is given by this expression. So I can evaluate how this, I can evaluate how the dynamics is going to work. So I know a great deal about what's going on in the system. And my algorithm is going to be closed, this implicit function theorem basically tells me that if these equalities are not quite equal, if this distribution mu's are not exact but in the vicinity, then the ends which I'm solving for are close to the ends when I have ideal values here. So this continuity I get from the implicit function theorem, which then I use to show my algorithm remains close to the fluid solution. So that helps me see a lot about how long the algorithm will take to converge. Those are the big ideas. So this is an example, index is small, I give it samples, this is rising, all these are coming down to a normalized index. When the two indexes meet, then they move together, meet the third index, they all meet until the right stopping time. So that's how the algorithm works. Okay, let me just tell you a little bit about. So by the way, everything I've said to you right now was for a single parameter exponential family, one parameter distribution. Very elegant theory on generalizing this to general distributions. So you get similar kind of problems. You have to look at the dual versions of these things. You have to bound them by mixture of super martingales, use Wheel's inequality. All of that nice work is needed because I told you these tubes and all, right? So concentration inequalities are crucial to all of this, but they require some technical analysis. That's a work we had done a couple of years ago in a different setting, so I won't talk about that right now. But let me talk about this thing. Estimating mean to epsilon accuracy with error probability less than delta. Simple problem. I generate IID samples from a probability distribution. I want to construct a confidence interval of with epsilon that should contain the mean with probability 1 minus delta. Right? I'll develop lower bound on this problem, and then one can develop algorithms which actually match the lower bound. That's the game here. So sequentially generate IID samples x1, x2 through x tau, the stopping time. Generate this confidence interval, you have L left-hand side, right-hand side. The gap should be less than epsilon, and they should contain mean with probabilities of 9. That's the requirement. And the technology I showed you works in this setting. It helps you think about these things. So we consider stable policies. So what we do is to make our life easy, we assume that these intervals, confidence intervals that we are coming to, as delta goes to 0. So this asymptotic limit of samples increasing was as delta goes to 0, I need more and more samples before I stop. So the regime I've been looking at is delta goes to 0. So I assume that the confidence intervals that my algorithm is allowed to have the property that these quantities will converge to deterministic number. So I restrict myself to those kinds of algorithms. That makes life much, much simpler. So once I do that, then I just say the data is from distribution mu. And suppose the data is employing a policy which gives me a confidence interval A and A plus epsilon. Because it has to be a with epsilon, right? So need enough samples to rule out that true mean is outside this interval. So I need to be convinced that the mean is not in this interval, basically. So basically I need e to the power 9, So A and A plus epsilon, this is what's truly going to happen. So if my mean is outside here, I should have enough samples to rule out that that this is not where the data is coming from. So basically it's going to be large emission between this guy, and large emission between this guy and this guy. So I'm talking a little fast, I can just say this very quickly. So if you want this quantity to be less than delta, the point is this: if I want an epsilon with confidence interval, typically when you do Gaussian approximation, you get symmetric confidence interval. Mu hat plus minus some fixed amount. But the best confidence intervals are obtained as follows. This is the Kullback-Leibler distance. It can be non-symmetric. This is the mean. You find the point epsilon, you raise this bar until the distance between the left side and the right side is epsilon. And that's your true confidence interval. That's what you should be approximating towards. And that's asymmetric. It can be different on this side, different on this side. But this is better than any other A and A plus epsilon. Because if I give you any other confidence interval, then you can see that this quantity is much smaller than this quantity. So it's much harder to separate this. You need many more samples to separate this guy. But this is the one which you can separate faster. So in any case, the punchline is that you don't want to get symmetric confidence intervals. You get clear symmetric confidence intervals in this sense. The Kullback-Leibler on both sides should be equal. And that's the right one. This theory can help you draw these kind of conclusions. All the things that we see in the banded settings for saying one is better than the other can also apply to developing confidence intervals for estimation purposes. Okay, with this, let me add Can you give me a moment or no? You need me. So I'll just say a few more things. Good time to take a nap, check your phone call. I show you fair amount of mathematics that you probably don't want to see. A lot of people will be very happy if they go right now, if they go 5 minutes later and see this slide, they hate me. Just don't do it. Just don't do it. Unless you really want to. Okay, because I've had those opinions. So again, we are back to best answer selection problem. So what I didn't tell you was how do we control the probability of error? I gave you an intuitive kind of lower bound, and I told you, okay, you chase the lower bound, it's one way or the other, and then you do well. But I didn't tell you that by doing things in this manner, the error that you will make will be bounded by probability delta. So that's a cumbersome exercise. Let me just give you some ideas behind it. So when do we make a mistake? So we stop when this happens, right? When this minimum amongst all the indexes, this quantity is bigger than log 1 by delta. That's kind of when we stop. All the indexes are, basically this means that all the indexes are bigger than log 1 by delta. I have enough evidence that none of these are the best ones. So we stop when this happens. But when can I go wrong? When I go wrong, meaning at this time, I reach the wrong conclusion. Some other arm is the best one. That means this alternate set actually contains the true configuration. Right? It's in the true set. The alternate set actually contains the real true solution. So this is going to be upper bounded by this true quantity right here. So instead of mu A, I'll just put in mu A here now. So if I can bound the probability that this guy here is not greater than log 1 by delta plus something small by delta, then I bounded the probability of making a mistake. Right? Because when I made a mistake, this event happened, and this event implies this event. If this event has probability less equal to delta, then this event has probability less equal to delta. And this is very nice. We know that mu hat A as a distribution is converging to mu of A. Right? So this probability, this term is going to 0, even when I multiply it by NA. So this quantity is going to 0. So this quantity taking a large value is a large deviation of sorts. So I can give you concentration inequalities, I can hope develop them, which exactly help me bound these things. So that's what takes effort. How do I bound these things? This Kullback ladder, which I defined for you, is actually solving an optimization problem. So I'll look at its dual representation and I'll do some more things on it, but let me just quickly do them. If you give me a moment.
We will have to take questions later.
That's why I'll just take some questions later. But okay, let me just say something very quickly. So instead of now looking at distributions which were like single parameter exponential family, I look at all probability distributions whose 1 plus epsilon moment has a known bound. So I don't know where my arm distributions are coming from, but I know their second moment is bounded by 10. This 10 number is known to me. Second and 10 is known to me. That's all I know about these things. So in this generality, I'll work, and in this generality, I'll define this proxy for the Kullback ladder that I had earlier. Earlier, I had Kullback ladder was mu A and nu. Nu is also a mean. Now nu is a distribution, but I look at all the distributions whose mean is bigger than x, and I find amongst them the most likely one, the closest one to mu A. And that I define as scale in for mu A and x. So this becomes a proxy. You show that it has all the nice properties, and much of what I've said generalizes with fair amount of technical effort. So that's a big idea. And the scale is that I defined for you, it's basically saying that, okay, I look at all the distributions kappa. I want to minimize my Kullback ladder distance. Under kappa, my 1 plus epsilon moment must be less than b, and my mean must be bigger than x. So this is the optimization problem that I'm solving for KL in reality, I'll have to look at the dual of this guy. And the reason I'm mentioning all these things is that when you look at the dual of this guy, you get a complicated term which you don't have to look at right now. But the complicated term is an average of independent things with this max sitting outside. This max of some parameters is a massively pain to deal with. So maximum of a function is generally a pain. But in this case, these functions have nice structure that you can bound the maximum by a mixture. So what I mean by that is maximum of these guys, GT lambda, exponential here, I can bound by log of this expectation here. So mixture has this nice property that if these terms were well behaved, then this mixture is going to be well behaved. What I mean by that is, if these terms are super martingales, then mixture of super martingale is also super martingale. So these ideas come into play here. That I look at super martingales, I sum up super martingales, they're also super martingales. I bound them by a mixture that's again super martingale, and there I can use this fields inequality. If you've seen some of these things, For non-negative super-martingale, because most of you, when you study probability, you do sub-martingale theorem. You don't do super-martingale theorem. But if you have a non-negative super-martingale, and then probability that the super-martingale ever exceeds x is upper bound by E of m0 upon x. So very powerful inequality. Nowadays, it's a common tool to bound these tube events. Probably you don't exceed the tube at any time. So this becomes a powerful tool, including an answer. That's what makes all the math work. I'll stop here. Thank you.
We are currently right now, so I would request if you have any questions, please.
Sure.
It's okay to.
Yeah, it's coffee right now. If somebody wants to ask, I'm here. Yeah.
And wonderful talk. You made it sound very elegant and simple, but once you uncovered the math, yes, it does look a bit scary, but yeah, definitely appreciated the talk. Thanks. I'm sure you have a lot of questions. I will have some questions too, but absolutely. Thank you.
Sure. This is.
So we'll meet here in half an hour. We'll be for the next session.
And the big point in these things is that if you solve easy, if you keep the underlying problem easy, you can go much more deep into it.
Right.
Otherwise,
Yeah, a lot of it is something that I know. But about the different aspects.
yeah.
I think practical application of very being able to solve